Welcome to the first of 4 short lectures on thermodynamics and equilibria. I am Rebecca Green and I am going to be delivering all of your lectures that you have for PM1B this term. So the objectives for this lecture is to introduce you to a few thermodynamic concepts, what a system is, so distinguishing between open, closed and isolated systems, potential energy and kinetic energy and their link to total internal energy, and we're going to define the first law of thermodynamics. All energy can be considered in terms of kinetic energy and potential energy, and these are terms you will have heard about before. Kinetic energy is the energy of a material or object due to its motion, and potential energy is the energy held by a material or object due to its position or due to stresses within the object. So in chemistry, this will be the energy within the bonds that form the structures. So we can think of energy in many different forms, thermal, electrical, etc., but all can be considered as either kinetic or potential. You may think of any energetic process as a combination of these. For example, thermal energy is a kinetic energy due to the random motion of particles, but there is also a potential energy component within the system due to the configuration of the particles. So how does kinetic energy and potential energy link to chemistry and to molecules? Well, we need to think about, first of all, the molecules themselves and their structure, which is where we will be thinking about potential energy concepts. So the actual structure of the active pharmaceutical ingredient, the excipients that are in our structures in terms of the other materials that we have within a drug system, like solvents, etc. And we also have molecular conformations, which is things like dissolution, partitioning between two phases, hydrolysis. So how does potential energy and kinetic energy link to these sorts of concepts? Let's start with an example of potential energy. So there are 2 ways of thinking about potential energy within a molecule. First of all, within a single molecule, there will be potential energy because of the interaction between the bonded atoms within that molecule. These could be electrostatic, and they could be due to the distance between these atoms. But there is a potential energy due to the energy of that bond. There's also intermolecular potential energy. So the molecules will be interacting with each other in some way, either within a liquid or a gas or within a solid structure. And so there will be interaction between the molecules. There'll be non-bonded energetics, non-bonded interactions, such as hydrogen bonding, you might consider as a non-bonded interaction, or electrostatic interactions between molecules. And these interactions all have potential to lead to change, to result in a reaction. So there is potential energy stored within the chemical structures, so within the chemical energies of these systems. But there's also kinetic energy because those molecules are not static. The bonds will be vibrating, the molecules will be moving in relation to each other. So the vibration of the bonds or the movement of the molecules between each other and around each other, that motion is the kinetic energy of the system. So our chemical system has potential energy in the bonded structures of the molecules and between the molecules, and it has kinetic energy due to the motion within the molecules and between the molecules. The total energy of a system is the total internal energy, and it will be made up of the sum of all the kinetic and potential energies within the system. And you can see this from the equation in this on this slide. The sigma term, if you don't understand the sigma term, there's some definition of that at the end of this lecture. But what this equation really is telling you is that the total internal energy, so U, is equal to all of the potential energies in the system going from molecule number 1 all the way up to molecule number n, and n is the number of molecules in the system, and all the kinetic energies of all of those molecules. So the sum of all the kinetic and potential energies in the system added together will give you the total internal energy. Almost every aspect of chemistry is governed by energy. And it is always possible to relate changes in internal energy to changes in the potential energy and the kinetic energy of the component atoms and molecules. Now you'll note there that where I said changes in internal energy, you will see the term delta, which looks like a triangle, U. Where you see that triangle, it means delta, so it means change in. And we will see it a number of times in different equations within these thermodynamics lectures. So the triangle is delta, capital delta, and delta U means changes in internal energy. So I've spoken about system a number of times, and so we really need to define our system. What do we mean by system? And in thermodynamics, it's important to define the system that we're talking about. If you have a reaction that's occurring in a flask, there are 3 ways that this reaction could be occurring. In an open system where it can exchange energy and matter with the surroundings. In a closed system where it can change energy, so it can change, say, heat energy from between the system and the surroundings, but it can't change matter. Okay, so it can't leak actual material from the flask. So a flask with a stopper on it. And an isolated system where you cannot exchange anything between the system and the surroundings. So the two are completely isolated from each other. And so you wouldn't be able to exchange energy or matter in an isolated system. So make sure you understand these 3 ways of thinking about our thermodynamic system. Now, in actual fact, it's not just as simple as, okay, I'm going to define the flask as the system. You also have to carefully think about what you're going to define as your system and what you're going to define as the surroundings. Now, to explain my previous comment about how you could define your system. Most observed systems are not actually isolated, as you know. When you think about an experiment that you would do in a laboratory, you know that that system isn't isolated. If you're thinking about the system as what is going on only in the flask. But it's usually possible, and it's often convenient, to treat the system and its immediate surroundings as your isolated system. So to define your system as both the flask and the immediate surroundings within the laboratory that the flask is sitting in. So as the observer, your system is everything that you can see in front of you. Okay. And this means that we can have exchange between the flask and what's immediately outside the flask, but you wouldn't expect there to be any thermodynamic change between, say, the inside of the room you're working in and the outside of the room you're working in due to that experiment. So there'd be no exchange with the rest of the universe. So defining your system as slightly bigger than just the flask means you can think of it as isolated from that point of view, which can help in some cases when you're thinking about how to use thermodynamics and thermodynamic concepts. So if we think about what we have learned so far, we have learned that the total internal energy of a system is the potential energies, all the potential energies and all the kinetic energies that we have within that system. And that we can also think about the change in potential energy and the change in kinetic energy. So these signs where I talked about the change in internal energy earlier, which is delta U, you can also say delta PE for the changing potential energy and delta KE for the change in kinetic energy. And it's easier to measure change in an energy often than to actually be able to get a feel for that, the total energy of a system. So what's the first law of thermodynamics? Well, this is what is often known as the law of conservation of energy, which means that energy cannot be created or destroyed. And what it means in terms of the concepts we've learned about today is the algebraic sum of all the energy changes in an isolated system is 0. And this means that the internal energy of an isolated system is constant. Okay, so it means that in our system, and in the way that we have defined our system as the flask and the environment immediately around the flask, you could have some heat transfer between just the inside and the outside of that flask. It's not going to go any further than that. Okay, and within that system, the internal energy is constant. Okay. Now, obviously, we're not that you can also define this concept in a much bigger sort of from the point of view of the universe, where the law of conservation energy means that you cannot create or destroy energy. You can only transform energy. And that is our bigger picture here. The universe itself is the ultimate isolated system. So according to the first law of thermodynamics, the total energy of the universe must be constant. So how does that fit with the fact that changes in energy most certainly do occur, e.g. in a chemical reaction? Well, it fits because we are not thinking about the entire universe or the entire system and surroundings when we're looking at those changes in energy. We're seeing transformations of energy. We're not seeing the loss of energy. We're seeing energy changing from one form to another, which is consistent with the first law of thermodynamics. So energies can change, but you can have transformation of energy, but you can't have a loss of energy. And the easiest example is the tennis ball. As a way of thinking about this, you might want to think of the tennis ball. So there was a tennis ball in a previous slide from today's lecture when we were talking about kinetic energy with the tennis ball moving and potential energy. So if you have a tennis ball high up and you're holding it, it has the potential to fall to the floor. So it has potential energy. And so that is the easiest way perhaps of thinking about potential and kinetic energy, which with your tennis ball. When you're holding it high up, the ball has potential energy. When you let go of it, it has kinetic energy. When it hits the floor, it will make a noise and there'll be a transformation of energy again. So this is a transformation of energy by the movement of that tennis ball. We've not lost energy in the system, we've just changed the form of the energy. Now in a molecular concept, we will see the same things. So let's think about the hydrolysis of aspirin in water. And let's think about this from the point of view of potential energy in the system, the kinetic energy in the system. So the bonds within this molecule, within aspirin, will all have potential energy due to their distance between the distance of the atoms between each other and the bonds that are holding the atoms together. And they have kinetic energy due to the movement because of the thermal energy within the system, the movement of the bonds. And also the molecule will be moving in water. So this is the energy of the system that will be transformed into a chemical energy in order to break the bonds and making bonds. So we are seeing a transformation of potential and kinetic energy between each other in this process. The bonds are being broken and formed and new molecules are formed. Okay. So we're taking the energy that's in the system already to enable this change, this molecular change to occur. So let's think about that in terms of our environment that we are doing this experiment in. So the total energy of the isolated system must remain constant. So if the reaction is in an isolated system, within that system, the total energy must remain constant. If we have a closed system, what does this mean? This means that energy can transfer between a flask where we have water and our reaction occurring and outside, so either heat moving in or out of the flask. But we can't have material moving. So that's a closed system. And in a closed system, then we don't have to have this rule that the total energy of the isolated system remains constant. The total energy, so U, total internal energy, of this closed system changes. But this just means that it is moving into the rest of the universe. The energy is moving from our system into the rest of the universe, or going from the universe into our system. So we're getting a transfer of energy between the two, but the total energy of the universe remains constant. So again, what's important here is a definition of your system. We often talk about heat transfer between our flask and the surroundings, and that can lead to energetic processes that we will talk about in the next lecture. But that is fine because we can define the universe, the system where the total energy remains constant, to be larger. So what have we talked about in this short lecture? We've talked about systems and surroundings, open, closed and isolated, and it's important to carefully define your system. And the first law of thermodynamics, so sum of changes in all the energies in an isolated system will be zero, which means that the internal energy is constant. Now there's a few slides at the end of this lecture that you can look through in your own time if you are very unsure about this capital sigma sign that you see in this equation here. If you've not come across that term before and you want to understand it, then look through the next 2 slides. I'll tell you more about that symbol that came up in the lectures today.